to mean any factor that would cause an equilibrium system to change. So we will use that same word. So any factor system to change. So we've already looked at a few things that will change an equilibrium system. What's one way that you can change an equilibrium system? Enthalpy is what drives it. Temperature. So if you change the temperature, you will change the equilibrium. So you can change the temperature. Anything else you think that could change it? Probably. Concentration. If you add some more of something into it, you will speed up the reverse or the forward reaction. So you can shift the equilibrium that way. And pressure. These will all shift in equilibrium. We're going to look at what they do and which way they'll shift it. Okay? So, what exactly did he say? I don't know if this is exactly what he says, but it's a paraphrase. If you stress a system that is in equilibrium, it will readjust in the direction that counteracts or minimizes the stress. Now that direction is going to change depending on what exactly the reaction is. Okay. So if we have hydrogen gas and iodine gas in a closed system, we let them come to equilibrium. So they'll produce 2 moles of HI gas, and then your equilibrium will be somewhere in the middle. All right. Then all of a sudden, we inject a bunch more H2 gas. Okay? What happens? So the H2 increases dramatically. The system freaks out. What do you think it's going to do if I jack this up? Which way is the system going to go? It's going to be pushed to the right. Because it's unstable, so it goes, I need to restabilize. So everything pushes this way. Okay? So it shifts in the direction that reduces the concentration of H2. That's its whole point. We added a whole bunch more H2. System freaked out, said I have to get rid of this, so it moves the reaction to the right, or the equilibrium to the right. Okay? So the hydrogen gas can be used up if we shift right. If system shifts right, or towards the products, to HI. So another way to say this is the equilibrium, well, I just said it, shift to the right, in order to reduce the stress of H2 added. So the shift right part stays the same, but we're just saying it's doing that to reduce the stress of the added H2. Now, it'll use up most of the hydrogen gas that you added, but it will never use up all of the hydrogen gas you added. So there will always be a slight increase, okay? So this part here is important. All right? Now I'll show you, you'll see this on the graph here in a sec. Most of it, but not all of it, will be used up of the new hydrogen gas. So if we look at the graph, if you graph this out, part A here, everything's at equilibrium. How do you know everything's at equilibrium? Just by looking at the graph. Constant concentrations. This is concentration. So all the concentrations are constant. Okay? So this is the equilibrium in section A. Then T1 happens. We inject the hydrogen gas. Okay? So hydrogen gas spikes. It just goes straight up. Okay? That's us injecting the hydrogen gas into it. System freaks out, goes, I have to get rid of this. So it shifts to the right. As it shifts to the right, that hydrogen gas gets used up in the reaction, so it comes down. But because it's going right, it's also using up I2. So the I2 concentration decreases as well, and the HI increases. Okay? And then it reestablishes equilibrium where everything is flat. Okay? The stress is being reduced as H2 is used up. I2 gets used up because it's part of the reaction, and HI is produced, and you get a shift to the right in the equilibrium. Okay? But note, we are still, even at equilibrium, the amount of H2 is still higher than it was initially. Okay? Yes. It would change the rate initially, right? Because you've got this massive concentration of this gets injected, and then it would reestablish equilibrium, and the rates would equal out. Okay. Your lab tomorrow is on this kind of stuff. All right. We won't use gases, but it's the same idea. Are we okay? I'm going to do one more example, and then we'll look at boiling water, because I know everybody's super excited for boiling water. We'll just stare at it right now. All right. Temperature changes. So we have PCl3 plus chlorine gas goes to PCl5 plus 92 kilojoules. Is this endo or exothermic? It's an exothermic reaction, right? Does entropy favor products or reactants? Does entropy favor products or reactants? Reactants, right? That's why we're at equilibrium. Because the products are favored due to the delta H, but entropy favors this because it's two gas molecules as opposed to one gas molecule. Okay. All right. What are we going to do here? So the forward reaction is exothermic. The reverse reaction is endothermic. So if we add heat into this system, we jack up the temperature once it's at equilibrium. Which way will it shift to counteract that increase in temperature? Well, to the right, heat or energy is a product, right? So if I add more heat or energy, the system doesn't want that. So it's going to push back this way. Okay? Like it's in a closed container, right? These are all gases, and then I heat up the container. Which way is this equilibrium going to shift? It's going to shift back this way to remove some of that excess heat. Okay. So the system can only reduce the stress, which is the heat, by engaging the reverse reaction, which means left. So the equilibrium shifts to the left. If we shift to the left, do we get more or less PCl3 and Cl2? If we go this way, you get more. So these will go up and this will go down. Okay? So PCl3 and Cl2 will have increased, while that will have decreased. So in the graph, here's the equilibrium. They're all flatline concentrations. You heat the system up, it shifts back this way. PCl3 gets produced, Cl2 gets produced, and PCl5 gets used up, so it decreases. What's the difference in this graph and the other graph? What does this graph not have that the other graph had? That's sort of a clunky way of me asking. Look at this graph. What happened initially? Yeah, there's no big spike, right? You get big spikes when you introduce something into the system. Okay? If it's just a temperature change, there's no spike, right? Because you're just going to push the reaction one way or the other. Okay? This is why most things, sort of unrelated, well, one of those questions in the last package, you don't have to write this down. You had this reaction, and the question in the last package was, why is this reaction endothermic? It's endothermic, right? Because this is just dissolving salt in water. Entropy is pushing it this way, but we know we reach a saturation point, which is equilibrium. So you know that enthalpy has to push back that way. So we know this has to be an endothermic reaction. So I'm just going to say plus heat or energy, doesn't matter. Okay? But what happens when you heat up water? Can you dissolve more or less of the salt in water? More. The reason that happens is because you're adding heat to the system. What does that do? It pushes the reaction this way, which dissolves more of that. Okay, that's why it has to be. If it was an exothermic reaction and you heated up the water, the salt would fall out of solution as a precipitate. Okay, there are things that are better dissolved in colder water, like gases dissolve better in colder water. Okay, but that's neither here nor there. Okay, there's only like 13 minutes left. We'll just fill out this last two little lines here. Section C represents the new equilibrium. Now there are more reactants because we shifted left. So these are higher, and less products because we shifted the equilibrium. We pushed it back that way. Okay, you can do, these are the questions you can do. You can do number 1, A to C and E. And while you're doing that, I'll set this up. I think it's just predicting what's happening.